Hello, everyone. Welcome to today's webinar. Before we start, if you could please raise your hand in the GoToWebinar control panel to indicate that you can hear us. Just make sure we've got good sound. Lots of hands going up. Thanks, everyone. Appreciate that. All right. During today's webinar, if you have any questions, please input them in the questions panel in the GoToWebinar control panel, and we'll answer as many questions as we have time for at the end. Today's session is being recorded, and we will send a link to the recording as well as the slides that are used today within the next 24 hours, so please watch for that email in your inbox. With that, I will turn it over to today's presenter. Ken?
Thank you, Terry. Hello, everyone. My name's Ken Cottrell, obviously. I'm based in Dallas. I've been working with GridGain and with the ML API piece for a few months now, so I very much look forward to our discussion today. So this is the agenda. So I'll give a kind of a brief overview of what is meant by continuous machine learning, and then I'll talk a little bit about the Apache Ignite, the architecture, and some of the recommended approaches, and then I'll show a quick demo with some API discussion and a little bit of software demo. So why machine learning at scale? I think that maybe many of you in the audience are familiar with what machine learning is and is not. So I think you know that a lot of the machine learning systems, at least up to now, that they've been based on a single server, maybe a big server with many gigabytes of memory. But as you know, lots of businesses today that they're getting into data sizes in the terabyte, even the petabyte range. And so taking that amount of data and then processing it so that you can actually get it to fit into these single server machine learning environments is very time consuming, that there's a lot of data movement and a lot of processing transformation that needs to be done. So there's three main, three main areas of bottlenecks kind of in the lower left-hand side there. So the first one, moving data out for training. As you know, that a lot of operational data nowadays is in a very finely tuned transaction processing system. What I'll call OLTP data. So these transaction processing systems, that they're very effective at doing transaction processing, but they are not suitable either due to lack of capacity or lack of data structure to co-locate the machine learning side of things. And this is true with any kind of analytics data. So as a result, you move the data elsewhere using these massive ETL extract transform load, or ELT as it's sometimes called, out to big data storage systems. So the data needs to be moved around. It's expensive in terms of time and usually in terms of the additional software. And then in the second item at the bottom there, wait for training to complete, that due to the fact that all of this data that normally sits in large clusters, that it needs to be kind of run through a machine learning algorithm that runs in a single server environment, that you need to downsample that data, and then you need to take very long training periods in many cases. I personally have been involved with some companies that took well over a day to do a single training run. And in fact, maybe even 2 days or more. So at the very least, it takes many hours, or it can take many hours. And so training can be a very complicated process, even when you have everything in the training system. And then last but not least, and this is another key aspect of continuous machine learning, is that you have to move the models back into the production transaction processing environment in many cases. After taking time to create the model, then now you need to go through another step to actually get that model back into production. Then you have to kind of do the reverse of what you did to move it out in the first place, that you need to like kind of reformat it into something that can be used for real-time or near real-time transactions. So this diagram, I think that this is fairly representative of what a lot of different organizations have to go through. So regardless of the technology used, that you're faced with a situation. You have raw data. The raw data may need to go through some kind of a cleaning and normalization process. And then this arrow, if you can see my cursor here, that this movement of data, all of these arrows potentially represents lengthy ETL processes. So maybe not all of them. Even for things that can occur within a single environment here, such as the learning, the model creation, the training, that this can still be lengthy just because of the fact that you're dealing with such a big volume of data. Even if you're not moving it over the network, you still have to somehow take chunks of this data from your persistence layer and then somehow get it through a learning environment. And then you compound that where this learning and this evaluation phase is lengthy. It requires a lot of think time. This feature engineering, which is done by the data science team, would greatly benefit by being able to spend more time actually thinking about how to deal with the features, as opposed to doing with all of the mechanics of moving information around and doing transformations. So, and then the last part of this whole process here, getting it back to the inferencing system. Those of you who've worked with machine learning in machine learning models know that the machine learning model, no matter how good it is, that it's going to drift over time, that the external data that it is meant to work with to do predicting and inferencing, that those conditions change over time, that the customer mix will change, the product sales characteristics will change, the external environment changes. And so the ability of an otherwise good model to accurately predict based on data is going to change over time. It'll become less effective, not because it's the fault of the model, it's just that the assumptions about the inbound data change. So ideally what you would want is a place to very rapidly get the model to where it can do inferencing, and then not only get it close to the data, but then to kind of track the performance of the model, not on a periodic basis, but actually on a much more frequent basis, that if it's possible, where every time you do transactions, or at least in very small batches of transactions, maybe 100 or 1,000 at a time, that you can actually see how the model is doing as the transactions are being performed. And so you get a better understanding of this drift as your operations are running. Okay. So anyway, I think this kind of illustrates the overall problem. So here's what we're advocating. So when we talk about continuous machine learning, and we say continuous machine learning at scale, because it's not just the fact that the machine learning is working on current data and is able to adjust to data changes, but also the fact that you can do it in a massively parallel environment, right? So think of this as being a simplification of the workflow I showed earlier, kind of the hardware, physical representation. You have a potentially a very high throughput, very well-tuned transaction processing system here, but because the data model between the transaction data set and the analytics data set is so different, both mainly in terms of normalization and things like that, and plus the fact that you don't have the capacity in a transaction system, that you have to pull it out. And so you have these ETL or ELT pipelines moving it into Hadoop here. Hadoop is good at storage. Hadoop is not a compute layer. And so even in Hadoop, you have to move it into some other kind of an in-memory compute processing system. And so you have yet another loading cycle here. You're doing maybe not so much data transformation, but you are pulling data out of disk and then pulling it into memory, and then you're passing it out to a cluster yet once again. So Spark is one that's very commonly used today. So Spark does a good job of the distributed training. However, at least in our experience, that there's still like gaps between what you do with Spark and then getting this information back to the app that needs to use that model. So there's still transference of data here and transformation of data that's required. So our approach with the Ignite platform, that with an in-memory compute platform, first of all, we deal with the scalability issue not by moving the analytic workload to another system. We deal with a scalability issue by horizontally adding nodes. Each node brings RAM and disk with it. And so you add workload capacity to this in-memory compute platform by adding nodes, and you leave the transaction data and the analytic data, the workloads, working on the same partitions. So it's not a single large box. It might be spread out over, say, 20 nodes, but you're splitting the data set into the 20 nodes, and you are splitting the machine learning workloads as well to run side by side with the data set. And so there's a number of benefits to this. One of them is that there is less of this kind of this impedance mismatch, since you can actually store and process everything kind of using the same parallel architecture here. It's easier to scale out. It is easier since the analytics data capability and the transaction are together with each other, that it becomes a much more kind of a real-time feedback loop. And plus, you can do more effectively, you can do the instant updates of these models. You don't have to do like a giant batch and then spend as much time rebuilding the model from scratch, that you can update it incrementally over time based on real-time measurement and tracking of how that model is doing. So I think some of you may have heard some of these new terms that have come out, such as the Hybrid Transaction Analytical Platform, HTAP or HOAP, and Gartner has started using the term Data Integration Hub lately, which we feel this is a very good representation of that whole approach. You have a single platform that does everything, and any automation that you want to put on top of this platform, such as AutoML or anything, that it gets the benefit of working with a single platform here, instead of having to deal not only with the machine learning workflow, but also with the physical architectural differences. Okay. So a bit about Apache Ignite. Our company actually got its start back in the early 2000s, and around the 2014 timeframe, our engineering team submitted Apache Ignite to the Apache Software Foundation. And within about a year, I think it was about 2015, it became a top 5 project after that. So it's been very well received. It's a very active community. Our engineering team, I'm talking about GridGain at this point, that we are a lot of the same people that work for GridGain as well as actively submit to Apache Ignite. So we have plenty of Ignite expertise in-house, but it is an open source product, and the demos that I'm going to show you are based on the open source product and not the GridGain commercialized product. Okay. As you would imagine, a lot of the companies that have been building their business on our Apache Ignite platform have been very large institutions with very stringent latency requirements, with very high resiliency requirements. Some of the companies here are running in the high hundreds, and I think even the thousands of Ignite nodes in parallel. So very large institutions, very large types of workloads here. So as you would imagine, financial services, telcos, software cloud, transportation, logistics, others with very large systems. So Apache Ignite and GridGain. So I work for GridGain. So GridGain is the commercial entity that we base our business, all of our products and all of our services on Apache Ignite. And so very commonly what happens is the open source community, people, individuals download Apache Ignite and they try it out and they like it. And then they come to us because they want to take Apache Ignite to production. So all the things that you see here, which are the things I'll be showing you, the core, the persistent data layer, the in-memory data grid, the in-memory database, the compute grid, which is our kind of our Lambda framework, and then the machine learning, everything that sits on top of this is the open source And then we as GridGain, that we offer support services for Ignite, that we offer more enterprise-grade monitoring and management, security, data center replications. So everything that has to do with manageability and security and SLA management in a large scale are what we add on. That there are additional modules that plug into the open source Apache Ignite framework. And then we also have a large number of adapters that we adapt, that we talk with market leading CDC systems, databases, of course, Kafka, Golden Gate, CDC, so you name it, that we have a lot of integration adapters that we also provide as part of the commercial offering. Okay, so let's talk now about specifically about Apache Ignite. So this is the stack. This is kind of a more detailed version of what I showed you earlier. So for this persistence layer that we run, and we are deployed both as an in-memory data grid and an in-memory database. So when I talk about an in-memory data grid, of course, I'm talking about a caching layer that sits on top of your oracles, your MySQLs, your SQL servers, your others, where we do read through and write through behavior to extend the reach and the throughput of an existing database. However, we also run side by side with that at the table level, depending on how you want to use it, as our own database. That we have a very high performance persistence layer. Where from an application perspective, it's going to look the same, that depending on how you want to structure a particular table, you can either have us sit in front of your Oracle, or you can have us sit in front of our own persistence layer. The persistence layer here is extremely interesting because every time you add a new Ignite node, it brings its own RAM and disk with it. And so you are growing the size of the data set you can imagine, deploy and manage in an incremental fashion. No architectural changes needed. You add a node, it joins the cluster, and then we rebalance and we extend the size of the cache or the SQL table as automatically as you want to set it, and then you've grown your application. So the compute grid, if you want to write microservices to encapsulate some of your workloads, you can do that. And then the compute grid, like I said, that it's a deployable Java object that is our Lambda approach. You bring a client, it declares, let's say it declares a new machine learning algorithm, it passes this out to the clusters, it finishes the training run, the client leaves the cluster, and then the cluster is totally dynamic, that it contains the data, and you bring new code online, you run the code, and you're done. And you can do all of these compute jobs on the cluster without making changes to the underlying architecture. Again, it's very dynamic. So the machine learning data sets are built on top of that. And then I'll show you all of the out-of-the-box algorithms and preprocessors that we bring to the table. In recent years, we've noted the acceptance and the growth of TensorFlow. So we originally did have our own neural network algorithms, but given that TensorFlow has gotten so popular and has so much momentum behind it, we're just advocating an integration. In fact, we built integrations with TensorFlow now that you might want to look at if you're doing those kinds of workloads. And then last but not least, all of the APIs on top. That we're seeing a lot of growth in Python. Since people want to combine the data engineering and the data science side. So we do have some Python pieces as well, but we also support a lot of the other low-level machine learning algorithms that you may want to use, including a thin client. If you want to create your own client in your own language, and we support a number of them, there's a JavaScript binding, for example, where you can use our thin client architecture. Okay, the core of the system. And this system, this replication and distribution duplication architecture is supported throughout the stack. So whether you're talking about an in-memory database, an in-memory data grid. If you're talking about compute grid, machine learning, all of our architecture is based on a partitioned and replicated architecture. I think this will be familiar to those of you who've worked with any other big data products like Hadoop or Spark, and so we use a lot of the same design metaphors. And so in this particular scenario, let's assume that we have a particular table, an SQL table or a key value cache, however you want to represent that. Let's say that it's 10 million rows total, and so each of these partitions on these nodes, and our partitioning mechanism ensures that it will be divvied up among the nodes so that you get resiliency. Assume about 2.5 million in 0, in 1, in 2, and 3. And so we will do all of that that partitioning for you based on the number of nodes. If you have more nodes, the partitions will have a smaller number of records. If you have fewer nodes, each one will have a larger proportion. So we do this apportioning with all of these data sets here. So the transaction data, the original OLTP data, any vectorizing, and I'm using the machine learning terms here, or any other compute functions, that they will operate the same way on this architecture. Very commonly, customers will have backups. So for any particular table or row that they want a backup of that row in another node. And so if you specify a backup of 1, then what that means is you'll take partition 0, 1, 2, and 3, and then you'll put them on different nodes. You can have as many backups as you want. Usually customers go with at least 1, but if you want more, you can do that as well. So what happens if node 2 goes down? So node 2 goes away. 1, the primary goes away, the primary copy of the record, and then 0, the secondary of partition 0 goes away, and automatically the system will say, okay, now the secondary number 1 in node 4, you will take over the role of doing transaction processing or machine learning or whatever, and then in node 1, 0 is already the primary. The rebalancing occurs whether you add nodes or whether you remove nodes. And so if node 3 goes away, the system will balance these caches so that you are still maintaining a backup. So node 0, all of these nodes that you see remaining here, they no longer have a backup. And so we will actually take that and we will split them up further so that they get backups. All of the rows get backed up over the remaining nodes. If the node is temporarily, if it's permanently down, if the node goes temporarily down, then you can set things up so that you don't do rebalancing if you know you're bringing the node back up, if it's due to some kind of maintenance or something, right? So to take that concept a bit further, when we're talking about the continuous learning, the machine learning piece, we do the same thing, that we use the Ds represent the data. Here, if you just assume that the Ds are your primary and a secondary backup, that the compute code, the Lambda, the Java deployable class, is it's declared in the client. It says I want to do a decision tree, or I want to do a random forest with the nodes, and so it passes that algorithm out to the primary and secondary. The training will run. That includes preprocessing, that includes taking the OLTP data and make it into a numeric vector, the training, and the redundancy here. What happens if one of the nodes goes down, let's say the primary, the secondary will continue the training on the same data. And so during the reduce phase here, you'll still get a result back. All the reduce phase wants the data from either the primary or the secondary. It doesn't care which one. So you don't have to restart the training role. Okay, so this is another aspect where training doesn't need to be restarted if it gets interrupted for any particular reason. So we maintain all of the context, the training context on both nodes, so that if one of them goes down, then you can still finish the reduce phase with the secondary. All right. So let's talk about some of the algorithms we support. So we include all of these, and so you don't you have the ability to add your own algorithms, but we provide a lot of the most common ones out of the box. And I think that most of the ones that you'll be needing are already here if you want to look at them with the open source product. So clustering, for those of you who are familiar with labeled and unlabeled data, so if you have a data set and you don't have labels, you don't know how to characterize it into groups, that the k-means and the Gaussian mix will help you do that. We provide both here. K-means is quicker and Gaussian is more thorough. And what you're looking for is you have this data and you're trying to say, you know, if we pick a k of 2 or 3 or 4, what is going to be represent the best clustering grouping for these? And obviously I'm showing a k of 3 here. You know, this is kind of a contrived diagram, but the k has to be tried out, that it's a trial and error thing. You don't know ahead of time until you run these algorithms. And then you'll get something that looks like this, you know, a small, you know, a gold, platinum, you know, silver or whatever, however you want to segment your customers, however you want to determine anomalous or conditions. If you run a network or if you run, you know, vehicle fleet or something, you can look for different clusters of behavior, various workload levels that occur. And then you can use this information to do the inverse, which is this is where you have labeled data. And now when you get new transactions coming in, you can look at the features of that OLTP data. You can pull out the features that are relevant. You can compare it to your model and say, you know, this is likely to be either a purple plus or a blue sphere, you know. And so again, things like fraud detection, you know, credit card scoring, clinical trials, all of the algorithms are included for you to try out, and all of these algorithms run side by side with your OLTP data, right? Regression, which is the a scalar output. You know, if you want to know a number, you know, price per square foot or other numeric or currency data, then you have a number of different algorithms here that can help with that. So businesses that want to do trend analysis, financial forecasting, response modeling, you know, in the life sciences, things like that. Okay, and then like I said, with TensorFlow, a very interesting and powerful algorithm. So a lot of these use cases here, this is all of the neural network approaches. And so when I talk about high dimension data, think of an image that's 100 pixels by 100 pixels. I mean, if you represent that as a vector, that is 100 times 100 or 10,000 columns. Many of them empty or sparse. Okay, and so that's where neural networks are really handy. So this isn't the same kind of OLTP, you know, transaction data necessarily. This is unstructured data, and so we provide the offering for this as well. So things like image classification, natural language processing, things like that. Now, I showed a little bit of the API here. If you're used to working with TensorFlow, that we co-locate that the way that you program TensorFlow is unchanged. If you're using the Ignite integration, that you simply pull in the Ignite dataset, our data partitions live on the same nodes as the TensorFlow cluster. And so these are all local imports here. And so once you do that, once you create the dataset, all of the things work the same way. It's just that now you've pulled in the data much more quickly since they're all on the same cluster. And so we also have some management tools to actually jointly manage that you create a cluster using the GridGain TF console product, and then you can group together the TensorFlow nodes and the Ignite nodes within a single framework so that you can manage them as a single cluster. Let's talk about pre-processing. So it wouldn't do a whole lot of good to have to pull data out of your OLTP system and then send it somewhere to do any kind of pre-processing or ETL or whatever, and then have to move it back into Ignite to do the training. And so we also do the pre-processing with the data. So for example, the normalization, which is something that will increase the predictive power of your model. So we provide that. We also provide scaling, which is something else that I think you'll find useful. I'm actually going to show how the scaling and the normalization actually improve the predictive accuracy of the data set later. So these are things that actually make the model better, but they need to be done prior to the training. So we can do all of those in place with the data. I went ahead and included a link here from Medium that I thought was handy because I was never clear on the difference between scaling and normalizing, but that might be a useful link to look at. Okay. Categorical values also need to be handled. And so you would choose between a one-hot here. Essentially, a one-hot is taking categorical values, red, yellow, blue, and in order to turn them into numbers, it has to create a column for red, a column for yellow, and a column for blue. And so that works well with with category columns that don't have very many values, but once you start getting to more categories, medical codes, for example, you don't want to be creating a big vector with a whole bunch of extra columns. And so we offer things like string encoding for those use cases. Kind of briefly talk about, so that's the overview of Ignite, the continuous machine learning at scale. So there are trade-offs. These trade-offs are things that you have to do for any kind of a big data or any kind of a data integration hub scenario, okay? So you're gonna have your operational data models that are centralized, that use referential integrity, that have foreign key constraints. They're very good with doing transaction system. In order to exploit a massively parallel architecture, there is a data denormalization step that needs to be done. So part of our service offering is when we are deploying our product on top of a relational database, or any database for that matter, NoSQL or Mongo or any of those others, that we do help customers kind of re-express the underlying data model in the database to be represented in a distributed parallel, read-through, write-through cache. And so there is an upfront cost to do that. There's also a data affinity methodology, a discipline that you go through. If you know that if you're working on a geographic application or a hospital application, and you happen to be doing joins, and you know that hospitals, which hospitals are going to be co-located, or that they're local to, the state of California or the, Los Angeles County, and you know ahead of time that certain joins are going to be doing that, you can actually place things within their natural parents, place tables within their natural parents, so that all of the queries and joins are occurring locally. If you're joining counties and cities and states in the United States, then you know that all the cities of California will always be in the state of California. So you can move all of the cities of California into that node where the state and county entities are, right? So this is how we guarantee the horizontal scale out. So kind of the second trade-off, and that this may require some thinking, that everything about the data partitioning and the computation needs to be done as much as possible locally within the node. If you have existing systems, then there is some thought that needs to go into this. The idea here is that you rework things so that the data shuffling that goes on over the network, either between the application and the cluster or among the cluster, may need to be kind of redesigned or re-implemented in some respects, right? But the payoff, of course, is that your computation, including machine learning, that can now work where it is with the data, so that everything is done locally, that you cut down on the network transmission time, and you're also going to cut down on some of the the transformation that needs to be done. And then last but not least, the pipeline enhancements. I think that the key here the 2 points, and this is kind of central to the whole continuous piece, is that you want to close the gap, make this ingest to inferencing a closed loop as much as possible. So this means dealing with the physical architectural aspects, but also dealing with the metadata, the data schemas and things. And so this is something, once you go through this first step here, moving from a centralized to a parallelized, which is a part of the data integration hub, scenario, that you'll be able to close the loop here. And then a big one to me is the fact that you can deal with the model drift, that you can actually have the model that lives with the data, and it's much easier to keep the model accurate, to measure how the model is doing as you run the business, that you don't have to, it doesn't have to be a back-end batch process, that it can increasingly move to more of a real-time, point of sale or point of customer interaction. Okay. So that's it. I have a few more slides. Let me show you, I'll just spend a little bit of time with the demo. So to get the demo, you just download, so these are the demos, first of all. There's a bunch of examples, free examples that come with Apache Ignite. So if you look at the Ignite package, excuse me, that we have like a bunch of, org.apache.ignite.examples. If you go into the examples directory here, you can import a Maven POM file. The ones I'm talking about will be in the ML package here. So we have a lot of examples that I've listed here where you can add your own preprocessor, you can add your own algorithms. You can work with TensorFlow. We don't include TensorFlow, but we include a TensorFlow model that we can parse. And we also parse other models such as XGBoost and others, so you don't have to have those, that we can't bundle them with Ignite, but we can at least bundle the model parses with them. And then the one I'm going to show you is this end-to-end training tutorial here, which walks you through in serial. And you can think of this as being kind of a poor man's auto ML here. So all of these are low-level things that would need to be done by any kind of automated machine learning. And we've done the hard part here, which is actually getting these to run in a distributed environment. That and I'll show you this. I run these all in serial here, but normally you would wrap this in some kind of a higher level machine learning, workbench, and then you could pick and select and then have these run automatically for you, and then you could see how well they perform. You could try different, hyperparameters, all those things, and then have us do the heavy lifting to actually run those out on your cluster. And I have Eclipse fired up, but before I do that, I don't really have time to show you the update model, but we do have the ability to update the model in place. And as you would expect, we have a model trainer with an update method, and you can pass in new data. The idea here is that you would have data caches that represent current or new data, a smaller one, something that's more, a smaller batch, and then you would do these incremental updates. There's different constraints on the ability to update models depending on the algorithm. So some of them lend themselves to that. The decision tree, that's one of the models where a decision tree doesn't really take that long to run. It's if you do it right. And so in many cases, it might just be quicker to retrain the decision tree. But a lot of these others here that are more time consuming, that they're more powerful, but they are more time consuming, that you can actually update them, and you can save time to when you're actually trying to tune the model to catch up to track with current operational data. Okay, so this is what I'm going to do. So I just pull in, and I wanted to write these down here. You'll get the slides so if you wanted to try it yourself. So you just pull in this POM file. I'm using Eclipse. I'm just going to run this in my laptop here. My Linux cluster is down, and so I'm just going to run it on my laptop and show you the output anyway. That we're using the Titanic dataset, which is available on Kaggle. I'll talk a little bit about the low-level API and how you can wrap it. If you want to, if you're a Java programmer and you want to do the machine learning in Java, but if you want something that's more UI-based, in other words, an auto ML workflow, then you can wrap that as well. And then I'm going to step through these, and then I'm just going to compare the different accuracy and some of the pros and cons with each one. And I'm going to do it using kind of a brute force approach, but I think you'll get the idea. Okay, so let me go to the, I went ahead and I ran this. I didn't want to take, you know, a couple minutes to run it. And so this is the code here. So this is the class that's in this particular, this is the tutorial. Here's all the other ML examples for you to run. These are all self-contained. And so, for example, with the, you know, the Titanic data, we just went ahead and bundled the data set in. It's small. And so the, if I look at the first one, this is the simple decision tree. So this is the first one that I run. And the API is pretty straightforward. So pretend here, instead of just reading in, I mean, we actually put the Titanic data set within the jar file. But if you just pretend that this is your big database system here and that you're just pulling in the cache that's sitting up in front of your database, it'll look exactly the same. Okay, so you declare the data cache, which may be sitting on 4 nodes, it may be sitting on 400 nodes. This is going to look the same. The vectorizer, what it does is it simply tells the machine learning algorithm which columns in the transaction data set do we want. And so we're pulling out columns 0, 5, and 6, which are purchase class, siblings present, and parents present. And then the label, column 1 here, refers to the did this passenger perish or did they survive? Okay, so this is how we're telling that, and this is a good example of something that you would want to automate here, but we provide the low-level API. So we're using a simple decision tree classifier, and then we're running the model. And so we do the trainer, and so the trainer, this is the part that runs in massively parallel fashion. That this trainer, you declare it here, it goes to it sends the Ignite handle to the cluster, you know, which points to the, you know, the particular cluster you want to use. You can use more than one cluster. Here's the data cache, the OLTP data, and then here is the extractor that says pull out these columns to use within the numerical vector. You run it, this takes a certain amount of time here, and then you evaluate it. So we do an accuracy calculation. For those of you who are data scientists, accuracy is useful for data sets that are not too imbalanced. That with a Titanic data set, I think that the ratio of the two classes, perished versus survived, is 2 to 1 or 3 to 1. Accuracy is not something that's terribly useful if you're doing fraud detection where you have 1 million records and maybe, you know, 1,000 of them are actual fraud. Then that's an example where you might use accuracy for some, but you would use some other measures like, you know, recall or precision or others that we provide. But this is suitable for what we're doing here with this particular data set. So this is the kind of the simple pipeline here that you point to the cache, you declare the column extractor, and then you declare the algorithm, and then you send it out to the cluster. All the map reduce is done for you. The results are sent back, or actually the results are done out at the cluster as well, pardon me, and then you can get the accuracy is going to be returned to you. In this case, it's going to be returned within this the predicate, you know, the predicate operator that we use with the Lambda calls. Okay, so that's how that works kind of in a nutshell. Let me show you what this looks like when going to the console. And actually, just let me show you these others here. So in building the pipeline, this imputer adds a missing value. The Titanic has a number of nulls in it. You can either you can read a data set without the nulls, or you can fill values in either a mean or an average, and that's what we do here. So all we did was we stuck this imputer in here to add missing values. Here in step 3, we are pulling in some additional values, so sex and embark. So you remember the you know, the women and children idea. And so we pull in some additional columns here, and then the gender is, of course, a categorical, right? Has a male and female, and then the embarked, I think, has 3 ports, some in UK, I think 1 in France. And so these are categories, and so we're doing a string encoder here, And then we do that, and then we're still doing the imputer, and then we're doing the trainer. So this is the pipeline that's being built up here. You can do all of these within a single class, but here we just kind of break them out into separate classes just for you know, illustrative purposes. In step 4, we add the age. Again, that should increase the accuracy. And then in step 7, we show what happens when you do overfitting, that all of these things here, that they were done without doing a train test split, and you get an artificially high accuracy, but then you fix that with the split train, okay? So like I said, I went ahead and reran this, and so I'm dumping everything to a screen. I'm running everything in a single JVM process, and I'm dumping everything to the console. And so I went in and I added a little text string here to show you kind of the what happens when you try these different algorithms. So the first basic decision tree accuracy is about 71%. Okay, not great, better than 0.5, but not that great. When we impute values, this goes up a little bit. I think it's like 712, so not much of a difference. So I'm guessing that the values that were nulls didn't really add that much value to the predictability anyway. Step 3, where we're adding the string encoding. This is where we're adding gender, and then that goes up to a 0.8. Okay, so just as you would expect, knowing whether the passenger was male or female would give you a better insight into whether the person perished or survived, right? If we go to step 4, we're using one-hot columns now instead of the string encoding. There isn't much of a difference. I think the fact that you add those, you know, the gender actually helped, and it didn't really matter in this case whether you used one-hot or string. Again, the reason you would use one or the other, it depends on the number of categories. That if you have a few categories, you can use one-hot, but if you have a lot of categories, you'd be creating a bunch of extra columns, and that doesn't aid the accuracy of the model. Okay. When you add age and fair, again, age, you know, the youth, that you see like a little uptick here that goes from 0.80 to 0.82, so just as expected. And I think also the fair, you just kind of assume that people who paid more probably had better access to lifeboats. Okay. Scaling helps too. So I think I mentioned scaling. I mean, the example in that link about scaling was along the lines of, you know, if you're doing financial instruments comparisons, you want to make sure that a dollar, something that's in dollar currency, being compared to something, you know, in a you know, yen, for example, you know, which is like 100 to the dollar, that a swing in the dollar value would overwhelm a swing in the yen value, and so the scaling helps everything work according to the same base. And so that actually made a significant improvement here in the ability of the model to predict. Now we're seeing, I mentioned this k nearest neighbor. This actually turned out to have quite a significant impact on the accuracy of the model. But you know what? Anytime you have a model that has an accuracy of 0.95, that kind of smells like overfitting, you know, unless you've done a lot of work, and we haven't done a lot of work here. We're just taking an initial first pass. And so you see the 0.95. Now what happens when we do the test train split? This is actually more accurate, that the split here, and it looks like this. I already saved it. Then we're actually adding a 75-25 split here, and so the training data is not the same as the test data, and so that's actually more accurate, because when you're using the same data for both training and testing, essentially the model is memorizing the training data, which is not good, you know, from an inferencing perspective, because that's not an accurate predictor for new data. Okay. And so that's kind of the, let's see, we're kind of down to our last, this is probably the best overall rating we can get here. So we're doing stacking and scaling. And so we're doing lots of things here. And it's kind of interesting that throughout the course of this demo here, that we've seen it go from like 0.7 to 0.8. which is good actually. So that's a pretty good improvement. 0.8 is actually pretty good from a you know, an inferencing perspective. And so instead of running all the steps manually, like here, like I said, you could have like some sort of a wrapper around this, you know, an Ignite service or something else that bundles all of these low-level APIs here into something that's more usable to a data science workbench, right? So one more thing I wanted to show you, and then I spoke about the inferencing piece. And so the inferencing here in this code, which we're actually creating a model, that we're running the model on a cluster, and here we're using a mortality data set. This isn't the same Titanic data set, that this is a healthcare mortality. This is already, I think, kind of in numeric format, and I think this is proximity of people to hospitals and doctors. And so we're pulling in the data set here. We're doing the train on it here. So we're training on the data. We don't have, you notice we're not really doing, we're not extracting columns here, since we can use all the columns as is. We don't have to filter out any, you know, unique strings or anything like that. So we can use all 4 or 5 columns. And then we're building the model, and then we're actually inferencing on the model all in one place here. So this is where you're actually, think of this as a potential example of how you can use the model to do a real-time prediction. So in essence, what you're doing, you have a transaction here that you're predicting the transaction, and then once you do the transaction, that you perform the sale or whatever, that you can take that, and you don't have to do this for every transaction, of course, but you can do it, you know, maybe in batches of 100 or something, that you can actually, in real time, you can see how you're doing, that you don't have to wait for a big batch run to find out if your model isn't performing as well as it used to. And so basically, if we run this here, and again, I'm just running this locally on my laptop. Normally you would do this in a big cluster, and so it's going to be a little bit slower, but basically it's going to do some number crunching on that data set, and then it's going to do the fitting, and then in addition to the fitting, it's going to do the inferencing. Okay, so while I'm doing that, let me go ahead. Okay, let's see. I think maybe it finished. Okay, so it actually did the comparison here. So like I said, my laptop isn't super fast, but basically it's actually doing these real-time predictions here. This model, it's okay, but you can see like some, you know, the difference between the prediction and the ground truth here, depending on your application, this might be totally acceptable, right? But I see that there is some spread here, you know, between the 9.6 and the 10.8. So depending on your application, that this may be something that's okay, but at the very least, you can see how the model is doing in real time here. You don't have to wait for some kind of a separate ETL load to an ML training system, okay? That is, let's see, I think I have one more slide to show you here. So I did have a chance to talk about Spark, but just like with TensorFlow, if you're a Spark developer, all you have to do when you're creating a Spark data frame is you write out to here, you just add some operator attributes from Ignite. You write, instead of being a regular Spark data frame, it's actually an Ignite in-memory table that's acting like a data frame. And so you have another Spark session later, or just a separate Spark session. You don't have to reread in from persistent storage to get this data frame, that this data frame is still alive and still ready to be read by another Spark session. So no matter how far in time or space these two Spark sessions are, that you still have this data frame waiting for you here. And then not only that, but because with our data frame, you do things like indexing, that you can cut down on the, you don't have to do scans on the data, that you can jump directly to your index here. You can see the index statement here where you're doing the key fields in the indexes here that we do for you. So just some internal numbers that we've done. This ability to read in-memory database data frames, that it can speed your data load times up by 5 times. That just some testing we've done, that it takes about 1/5 of the time in a Spark pipeline to read from our data frame. And then in terms of these SQL queries here, that you can do these queries in maybe twice the speed. I mean, a Spark is still fast, but it's not indexed like we are, and so our select statements, all of the SQL statements, can be correspondingly faster. Okay, just to summarize, that we meet the definition of this. If you haven't heard of digital integration hubs, read up on them. That's the future. Actually, it's not the future, it's today. I mean, you have the tools to build them today, where you can eliminate a lot of the ETL work that's going on, and correspondingly, you can close the gap between the operational data and the analytical workloads to better run your business. And then aside from the ML side of things, that with Apache Ignite, that we bring the massive scale more so than other approaches. That it's a massive scale, massive speed, everything, memory, storage, computation can be done in a massively parallel environment. Plus, we have lots of integrations with existing machine learning and deep learning operations. That it's not about rip and replace, it's about extending and empowering the investments you have with an in-memory compute platform. Just some resources, and I guess I think we're down to 4 minutes. Terry, if you want to open it up for questions.
Yes, thanks, Ken. Again, if you have a question, please enter it in the questions box in the GoToWebinar control panel. We'll give just a minute here for any questions. Okay, well, looks like we don't have any questions for today. So again, oh, wait a sec, we do have some questions for today popping up here. Let's see. One question is whether there's any support for GPUs in Ignite planned or coming up in the future.
I believe I haven't worked enough with the GPUs. I know that we're working with Intel and some other vendors to take advantage of hardware. I don't know which GPUs that's that we're working with, but I'd be happy to follow up on that. But we're definitely doing work at the hardware level with vendors, and I know of Intel in particular. I just don't know about some of the other vendors. So yes.
Okay, great. And that pretty much brings us to the top of the hour. Again, today's session was recorded, and we'll send a link to the recording and to the slides here in the next 24 hours. So please keep an eye out for those. Thanks everyone for attending, and thank you, Ken. Have a good day, everybody. Goodbye.
Thanks.